With lenses, we have two different types of lenses. The first type of lens we'll look at is a converging lens. So with a converging lens, you're often going to see it drawn like this. And it's going to be kind of the shape that lets you know it's a converging lens if you see it in a picture. And as light travels through here, right, we usually draw a line right through here to kind of indicate the middle of the lens. As light travels through here, what's going to happen is because of refraction, all this light is sort of going to be converging, that's where the name comes from, to sort of a single point right here that would be what we call a focal. With a diverging lens, we get something like this, where it's more this shape, and what that's going to cause is that light that comes in is going to be reflected sort of all away from it, straight through the center, and away as light comes in. But if we were to sort of trace these lines backwards, they would all trace backwards to a single point that would be the focal point of that lens. And so what we want to look at is these two lenses and how we can sort of draw light rays to predict what sort of images they can form. So let's look at the case for a converging lens, or at least one case for a converging lens. So we'll have our lens here, and we also want to draw a line down the middle of our lens to sort of indicate where the middle is, because that's where we're actually going to draw our light bending at. All lenses have two focal points, one here and one here, and they're an equal distance away. And we usually draw our object as an arrow. The reason for that is because we can see sort of which direction it's pointing, so we can tell whether an object gets inverted or not. So we have three lines that we would draw with a ray diagram to see where our image forms. The first one that we can draw is light that comes into the lens parallel, and light that comes into the lens parallel is going to get reflected through the focal point on the other side. I can draw light that goes through the focal point on this side and hits the lens, and then that is going to be reflected parallel. And then I can also draw a light ray that goes through the center of the lens. And if I've drawn this all well, especially with a ruler, all that light should converge on a single point here. And so by drawing those lines, I now know that the image that's formed is going to be here and inverted. So this is what we call an inverted image. And it is also what we call a real image. So there's going to be real and virtual images. A real image means that the light is actually at that location where we're seeing the image formed at. In other words, if I put a piece of paper right here, because the light's there, I actually get a projection of that image right there. The other case that we could have for a converging lens, so let's get our lens back here. There's the middle of the lens and our focal points, ideally an equal distance away, though it's kind of hard to draw without a ruler, is if the object is inside the focal point of our converging lens. So our first line is the same, parallel and then through the focal point. The second one's a little trickier though, because I can't draw light that goes through the focal point and then through the lens, because light travels in straight lines and doesn't bend like that. But what I can draw is light as if it came from the focal point and then parallel. And you'll notice that those did not meet up. We'll get to that in a second. And then light that goes right through the center. Now, none of the light converged over here. So you may think that you wouldn't see anything, but that's not quite true, because your eye sees light as traveling in straight lines as well. And so it's actually going to sort of trace those back to where did that light come from, and that's sort of where it sees the image, even though it's not actually there. So what we're going to do is we're actually going to take all of these lines, the refracted lines, and trace them back. So if I trace this line back, and trace that line back, and trace my center point back, Again, ideally, if I were using a ruler, they would all meet up at a point here, and there is my actual image. You'll notice it's magnified. It's much bigger than it originally was. It is also upright, unlike the last one, which was inverted. And it's what we call a virtual image. If I put a piece of paper right here, there's no light there to actually make that image. It's just if we're looking at this object from over here, our eye is perceiving that light is coming from that point, and so it's going to, tell your brain that that's where the object is. The light isn't actually there, which is why we call it a virtual image. And what we see is actually kind of a pattern with converging lenses and with lenses in general. If we have an upright image, it's always going to be a virtual. And in our previous example, if we have an inverted image, it's always going to be real. And that's always going to be the case for these problems with just a single lens. For a diverging lens, there would maybe be the center. Right, now our lens is going to curve this way. Again, we have two focal points. Just like before, we try and make those sort of the same there. If we look at the case for outside the focal point, here's how we draw it for a diverging lens. We have our light going towards the center, and then it gets reflected away. It disperses the light, and so we're going to picture that light as being bent as if it came from that first focal point. Our third line is we would have light as if it were going towards this focal point, but then hits the lens and gets refracted parallel. And then, as always, straight through the center. Now you'll notice again, none of our points met up, which means we're going to have to trace all of our lines back. And if we did a good job, we'd see that our image forms there. That image is upright. And because there is no light actually there, we're just sort of tracing those lines back, or our eye is as it looks at it. It is also a virtual image. Now let's look at the case for a diverging lens that's inside the focal point, where our object's inside the focal point, since last one was outside. So here we'll put our two focal points and our object somewhere in the middle. So our first line, parallel, and then as if it were coming from the focal point, so no difference there. And then the next one as if it were going out to that focal point, and then refracted parallel, and then through the center. And then again, no light converges on the other side, so we're going to trace everything back. Ideally, they meet all at one point. And there we again get an upright virtual image. So you'll notice a diverging lens only creates virtual images, right? Whether it was inside or outside the focal point, we ended up with a virtual upright image. The only difference was before, when we were outside the focal point, we ended up with something that had a big magnification to it, a positive magnification, and here a negative magnification. It made our object smaller. So that seems like a lot, but there's some general rules. If you can kind of remember these three general rules, it's going to at least get you a start with your ray diagrams. Remember, we're always going to start with light that goes parallel and then to a focal point, or from a focal point to parallel, and then a line through the center. Those are always the three rays we're going to draw. Now, they're slightly different depending on each situation, but those are sort of just the general works for everything sort of rules. Parallel to focal point to parallel, and a line through the center. The important thing about drawing ray diagrams, if you draw them to scale, it actually represents what's going to happen in real life. So drawing and measuring these things with rulers actually tells us something that calculations would tell us just as well. So we can solve problems by drawing ray diagrams. We can also solve them with equations. And our equation looks like this. 1 over d naught, or dO, plus 1 over di equals 1 over f. And what these stand for, d naught would be our object distance. In other words, how far is our object from the lens? Di would be the image distance. which is how far away from the lens is the image formed, and f is our focal point, right? How far away is the focal point from the center of the lens? And so we could calculate, where things are located that way as well, other than drawing a ray diagram. We can also find image height or object height using magnification, which can relate to our image and object distance. Negative di over d naught equals magnification. Now, the signs here are kind of important, the negatives here. For example, if I have a negative magnification, that means that my object is inverted. Positive would mean upright. And kind of, if you think back to your lenses, inverted always means a real image, upright means a virtual image. So that whether it's upright or inverted can tell you a lot about the lens and the image that's going to be formed from it.